Quick disclaimer before starting the video. I'm sorry if you hear a little bit of background noise, but I have a fan going right here, and it's the only thing that keeps me alive with this temperature here in Italy. So I'm sorry for that, but you're gonna have to live with that. The transformer architecture became really famous after 2017 with this paper, Attention is all you need. Google published this architecture a while ago, but it's still what nowadays runs every big large language model like ChatGPT or Claude or DeepSeek. The transformer is this architecture right here. It's a deep learning architecture. And I'm not going to go through the details of it. I assume that you're already familiar with the transformer. There are a ton of videos out there and a ton of content, and I'm not going to explain it once again. I'm quickly going to review the decoder part in a few minutes, and that's because what we are interested for the sake of this video. Okay, so let's review the architecture of the transformer decoder from 2017 Attention is all you need paper. So, as I said, LLMs, so large language model, are decoder-only transformers. So we are going to basically get rid of the encoder part, which is this part right here, and we're going to focus only on the decoder part. And this is actually what happens in many of the modern architectures. Encoder, decoder, transformer-based architectures are less and less frequent and less popular, and people are just starting to use a single stream, let's say. So the decoder back then was made like this. So the text was tokenized. So for example, you can think of the sentence, where is Rome? And you can think of tokens as words. This is a very common thing that we do to simplify things, even if it's not true. For example, byte pair encoding does not tokenize the text by words. It tokenizes the text with bytes, and it's a lot different. But for the sake of simplicity, usually what we do is we think of tokens as words. So the tokens basically are indexes. They're just numbers. They are indices in a vocabulary. And the first step is obviously to create the embeddings. And basically, you can picture these as each token, so let's say an index, I don't know, 32, basically maps to a vector of real numbers. And this mapping is just stored in a matrix. So you can picture it like this for simplicity. Then, after the embeddings are obtained, what we do is we add the so-called positional encoding. The positional encoding is information that we inject inside the transformer, because every operation that we do inside the stream, the transformer stream, is invariant to position. So this is a way to inject positional information in an architecture which does not have any positional bias inside the operation that it does. At the beginning, this positional encoding was basically a function. It was based on sinusoidal waves, so sine, cosine. But nowadays, this is basically just a learned vector. So it's just a vector with the same dimensionality of the embeddings, and it is just added to the embeddings, and gradient is backpropagated through it so that it is learned. Okay, so after the embeddings are ready, so after the positional encoding, we can get inside the transformer decoder. So transformer decoder, so back then, if we look at this architecture here, it has self-attention, cross attention and feed forward. Right now we will not consider the cross attention because we don't have the encoder part. So basically what happens is we only have the self attention here. Then we have the add and the layer norm, and we have a residual connection right here. Then we're gonna have, so as I said, let's write it anyway. So as I said at the beginning, we add the cross attention, and the cross attention takes the query from the decoder stream and the keys and the values from the encoder stream, which is outside. Then we have again add and layer norm, and we have a residual connection, and then we have again the we have a feed forward layer, and again layer norm. And then after this, obviously we take the output of this last layer, we apply a linear layer, so just a linear projection. Then we apply the softmax row-wise, and then we take, in the transformer decoder, we take the row corresponding to the last token, and that would give us the probability, the probability distribution of the next token in the vocabulary space. So basically what we have in output is a discrete probability distribution like this. And let's say that our last token, so let's say that we forwarded all of this through the transformer, and what we expect in output is like Rome is in Italy. Then if we forward all of this sequence through the transformer, our output will be a probability distribution over this token right here. And so basically if our transformer worked well, if our language model worked well, this one will be the probability of the token Rome. So the transformer architecture evolved slightly from 2017. Since this architecture became so popular, people started optimizing it, and right now we converged to this architecture right here, which I'm going to describe now. So we have our embeddings. We go inside the transformer decoder. As I said, since we are in a decoder only architecture, we are not going to consider the encoder part. So the first thing that we have here is a layer norm that is applied immediately. Then we have the multi-add self-attention operator. Then we have the addition of the residual connection, which basically comes from here. Then we're gonna have a feed forward. We're gonna have another layer norm here. Then we have the feed forward layer, and then again the addition of the residual connection. So this is our modern, let's say, transformer decoder. A couple of things to note here. Obviously, as you can see, we only have one attention operator, which is the multi-add self-attention. We don't need cross-attention anymore, since we don't have the encoder. And as you can see here, layer norm are applied before before the layers, basically, and before the multi-add self-attention and before the feed forward. And well, obviously here at the end we go out, and then the head is applied, let's say. And then here the feed forward is looks like this. If we sort of zoom in that one, it's going to be an MLP followed by a, well, actually a linear layer followed by a non-linearity, a non-linear function. In this case we use the GELU. Then we have another linear, and then we have the dropout. Okay, so let's now take, for example, the GPT-3 implementation of the transformer, which was published by OpenAI in 2020. And let's take specifically the biggest model that they published with that paper, which is a 175 billion parameter model. Okay, so let's count how many bytes are needed to store such a big model. So if we only consider the model weights, in modern deep learning frameworks, weights are stored both as FP16 numbers and also FP32 numbers. The FP32 version of the weights is called the master, and the FP16 are basically just copies. And so basically, if we add these two together, we have a total of basically 6 bytes per weight. So if we do some approximations, we can see that we have, so if we multiply 175 by 6 basically, because we need 6 bytes per parameter, and then we are in billions, so we multiply by 10 to the 9th power, and we divide, so to get the number of gigabytes, what we would do is we need to divide by 124, 124, 124, and this is more or less 10 to the 9th power. What is happening? Okay, I'm sorry for that. 10 to the 9th power. So we can just do this. So this is basically almost 1,000 gigabytes of memory. So this is basically the amount of space that we needed to store only the weights of our model. And obviously here we are considering both the master weights and the FP16 copy of the weights. So we are actually considering, we are imagining that we are in the training scenario, not in the inference one. So when we are doing inference, usually we quantize, so we apply quantization, so we reduce the precision of our floating point numbers. Or for example, we can only use the FP16 version of the weights or only the FP32 version of the weights. But during training, we need this amount of memory just to store the model parameters. Then we would also have to consider the gradients. We will also have to consider the optimizer states and also the intermediate activation. And this is like even more space that we need to use. So this was just to show you how much gigabytes we need to store and work with these models. Okay, so let's now jump to the main topics of this video, which are pipelining and tensor parallelism. So, as you all know, large language models are run on GPUs. Again, this is not going to be a detailed video on how GPUs work, but all you need to know for the sake of this video is that GPUs are very good at parallelizing work. That's because GPUs are they have a ton of cores, and each one of those cores can perform really efficiently arithmetic operations. And if you think about it, yeah, obviously in parallel, and if you think about it in deep learning, all we do is matrix multiplications, so those are very efficient to offload to the GPU. The problem is that nowadays, even like the largest GPUs, maybe they can, if we take for example very expensive GPUs, they have like 100 gigabytes of VRAM. This means that they can basically store, let's say, 1/10 of the GPT-3 parameters. So what about the other 900 parameters of GPT-3? How do we store them? How do we store those matrices inside the GPUs? So obviously, it's very clear that one GPU is not enough. So we need a way to parallelize work and to sort of make GPUs talk together and work together to store these very big models. Okay, so let's now focus on pipelining. The most naive thing that we can think of is we take the transformer. The transformer stack is made of, as I said, L layers. Let's say, for example, 96 layers. The easiest thing that we can think of is, let's just split the transformer in sections like this. For example, we have 1, 2, 3, 4 sections. And then we take 4 GPUs. So we have one GPU here, one GPU here, one GPU here, and one GPU here. And we're going to store the first block of parameters in the first GPU, the second block in the third block in the third section, and the last block and the last parameters in the last section. And then we are just, let's say that we have our 4 GPUs connected with some cables. Okay. Think, for example, that you can imagine that they are connected through like in a ring structure like this. So basically, when we have our embeddings, we forward it through the first stack of the transformer in the GPU1. Then the GPU1 does its computation and will send the hidden layers, the hidden representation to the second GPU. Then the second GPU will send its output to the third, and then the third will send it to the output to the fourth GPU. And here we can gather the output. So this is the main idea behind pipelining, and you can usually what you find in textbooks or articles is they say they split the model vertically. And that's because if you think about a neural network, what you do is you just split the model like this. Okay, so like this, for example. Okay, so you do the first part of the computation in one GPU, then the second part of the matmul's in the second GPU, and then the third. That's why they call it a vertical split. Okay, so let's draw everything in a slightly different way, which will help us with some concepts. So as you see here, I draw this very big grid, and imagine that on this axis we have GPU. So we have GPUs. So we have a first, second, third, and fourth GPU. So these are our devices, called in more technical terms. And then here we have the time. So the naive thing that we did before would look something like this. So we have the forward pass. So let's say that our the first step of our forward pass will take 4 time steps. Okay. And on the second GPU will take as well 4 time steps, and on the third will take 4 time steps, and the same for the fourth. Okay, so what I've drawn here, just to be clear, is the forward pass. Remember, when we're training neural networks, we also need to compute to do the backward pass, because we need to compute the loss functions, the loss function, then the gradients, and then do the weight update. And usually it takes a little bit longer. And let's say that it takes eight blocks, and it's even like we don't even have enough space, but okay, 8 blocks, so it goes out here, and then I can do the backward pass of the second for the second GPU, and so on and so forth. So as you can see, it takes definitely too long. We need to do something to sort of compress to sort of shrink the time spans here. So let's just erase the stuff. Okay, so the core idea here to optimize pipelining is to do something like this. So the big rectangle that I've drawn before was the batch. So the batch of data that goes through our model. So the batch will be, what we can do is we can split it into smaller batches, which are going to be called micro batches. And now we can leverage this split and do something like this. So the first GPU maybe computes the forward pass for the first micro batch. Then it goes to the second. While the first GPU is computing the second micro batch, we can, in the second GPU, start with the first. And then while the first one is starting the third, then in the second GPU I can start the second. And in the third one, I can start the first. So if you think about this, we can fill our table this way. Okay, so as you can see, while the first GPU already computed the full batch, the forward pass for the full batch, the fourth GPU already finished the computation for the first micro batch. And now what we can do is, now the fourth GPU, as you can see here, is ready to compute the backward pass for the first micro batch. Okay. So while the last GPU is computing these, is computing the backward, is doing the backward, then we can finish filling these so that we are aligned. And now the first micro batch, if we speed things up a little bit here, basically will flow this way. So first, well, here I think I'm missing a line. Let me just fix this very quickly. Okay. So we will fill things up here like this. And so we went a little bit forward in time here to speed things up. But now, when the last GPU finished the backward for the first micro batch, can start the computation of the forward of the second micro batch. And then things will go accordingly. And then for the third. And as you can see here, we are overlapping computation, and we are optimizing a lot more. So here we have fourth micro batch, and which is the last one. And as you can see here, we successfully computed the forward pass and the backward pass for an entire batch. In you know, we have like we are in bounds, let's say in the limits. Before, if you remember, we basically were starting, like we finished the forward pass right here, and then we didn't even start the backward pass, so we are a lot faster this way. And this is the core idea behind pipelining. So as you can see, the main concept is that GPUs can, let's say, compute things asynchronously, and they can, let's say, already do work if they have data available. They don't always need to wait for the full batch or for the full backward pass, so they can already start if they can do something. It's basically the same concept that happens in CPU pipelining, if you're familiar with that. One last thing to note is that this is obviously not optimal. As you can see here, we are creating, we still have some bubbles where nothing happens. And there are some more difficult slash interesting slash hardcore, let's say, pipelining strategies. For example, dual pipe, which was used in DeepSeek R1, I guess. And if you're interested in pipelining, definitely go out and check the DeepSeek code, which basically goes through the dual pipe procedure. But obviously, I mean, this is not necessary if you just want to understand what pipelining is. Okay, so let's get to the second topic of this video, which is tensor parallelism. So this is another way of offloading matrix multiplications to GPUs in a way that is distributed. So we distribute the work across GPUs. This time we do it in a slightly different way though. If before, basically we were splitting our model vertically, so like this, and data flow, the data flow was like this, so the input was here and the output was here, and our split was by layers like this, vertical split. Now in tensor parallelism, what we're gonna do is we're gonna split horizontally. And this might sound a little bit weird at first, but don't worry, we're going to go through the math together, and I will try to be as clear as possible with this. Another quick disclaimer: if you're interested in this technique, I really encourage you to read this paper, Megatron LM. It is a paper from NVIDIA where they describe this technique in detail. And it's actually a pretty clear paper, and I think it's worth reading if you want to know and understand how parallelism and large-scale training works. Okay, so let's take, for example, the case of a simple multilayer perceptron. In an MLP, what we do is we multiply x by w, and then we apply nonlinearity, like a GELU in our case. So x is obviously our input, and w is the weight matrix. So x has shape n by big D, while w has shape big D by small d. And where obviously n is the sequence length, and d is usually the model dimension, model dim, and d is the hidden dim. Well, usually these are like I'm using the notation that they use in transformers, but sometimes it changes slightly, so you, depending on the paper that you land on, you find different notations. I will just call them big D and small d. And that's because usually in multi-layer perceptron, what we do is we take, let's say, a high dimensional vector. What is happening? Okay. We take a high dimensional vector and we want to map it to a smaller dimensional vector. So for example, this, let's say, is a shape big D. We want to sort of compress it into a smaller dimensional vector. So obviously, if we do our, if we call this Z, so the output is going to be Z, then Z is going to have shape of big N by small d. So the core idea is, okay, let's try to parallelize this specific operation. So let's say that we have, let's assume that we have just 2 GPUs, and we want to make some computation on one GPU and some other computation on the other GPU. One thing that we can think about, so that the first, let's say the first approach that we can have is, let's split X by columns, and we split Y by rows. Okay. So if we split X by columns, I mean something like this. And W is going to look something like this. Okay. So let's call, so before obviously this dimension here was big D, and this was N. Now let's call this K. So obviously 2K then will be equal to D in this case. And in the same way, W had shape big D by D, so this thing is K and this is D. So how do we, so let's say that we send X1 to GPU1 and W1 to GPU1 and X2 and W2 to GPU2. So what we're going to do is, in GPU1 we're going to compute X1 by W1, and with X1, which is N by K, and W1 is K by D. So our output, so let's say Y1, yeah, let's call it Y. So Y1 is going to have shape, is going to have shape D, sorry, N by D. And similarly, on GPU2, we're going to do X2 by W2. And we call this Y2, and this will be of shape the same, so N by D, N by small d. So now to obtain the final output, obviously the thing that we have to do is we have to sum these two matrices. So we have to do Y1 plus Y2. Then once we sum these two matrices, we can apply our GELU. Okay. So, but remember, Y1 is on GPU1 and Y2 is on GPU2. Okay. So this means that before applying the GELU, we need what is called a communication step. So we need either one of the GPU, we can call it the master GPU, to gather the outputs of every GPU, in this case only of GPU2, and sum internally the two matrices. Then it can apply the GELU. Somebody can say, but what if the GPU just compute GELU separately? So GELU of Y1 and then add GELU of Y2. Well, we cannot do that, unfortunately, because GELU is a nonlinear function, so we cannot apply GELU separately to the two pieces and then add them together. So this is something that we cannot do. So we need to do this. So we need this communication step before the GELU. So in the second approach, we are going to not split X, and we're going to split W by, so before we were splitting it by rows, this time we split it by columns. So X is just going to be no split on X, but W we're going to split it this way. Okay. So now what we can do is the following. So we can send, so we have GPU1 and GPU2. GPU1 will take X and GPU2 will take X. So we're going to replicate X this time on the two GPUs. And then on GPU1 we're going to do X multiplied by W1, and on GPU2 X multiplied by W2. So this is going to be Y1, this is going to be Y2. And then Z1 and Z2 are going to be the GELU. Z1 and Z2 are going to be the GELU of Y1 and the GELU of Y2. And then our final answer, Z, will be just Z1. And then we concatenate Z2. So let's go through the shapes so that we understand things better. So X multiplied by W1. So we have X again is N multiplied by big D, and W1 is D multiplied by K, right? XW1, which is our Y1, is going to have shape N by K, by small k this time. And the same thing is going to be for W2. So if you think about it, this time, in each GPU, we are not computing a full-sized matrix. We are computing a piece of the final matrix itself. So only 1/2, let's say, in this case, of the final matrix. So at the end, when we gather all of the information, then we can just concatenate the pieces together. So in this case, we can actually apply the GELU after the matmul, because what we have inside the GELU is just the final piece of our matrix. So we can apply it, and the result will be the same. So what we did this time is we have the two streams. So we do the matmul here and the matmul here. Then we apply the GELU separately, and then we gather at the end. What we were doing before instead in the first approach was matmul, matmul, gather here, and then apply the GELU. Okay, so to better understand why the second approach is better than the first, we go through a real example, so a real multilayer perceptron, which is applied in the transformer architecture. And we will see that delaying the gather step in the first part will be better when we actually get into the dropout. So the first part here is exactly what I explained before. So we just do a matmul x by a. This time the weight matrix is called a, and then we apply the GLU nonlinearity. And in this case, they call y the output of this step. I call that z, but this time they call it y. And as you can see, x is replicated in the two GPUs. Then the matmul is done. Then the GLU is applied to each single piece of the matrix. And then in output we have y1 and y2. So our final matrix looks something like this. This is y. It would be y1 and y2. The only thing is that y1 is on GPU 1 and y2 is on GPU 2. So why is it better now? Because since we don't need this, since we don't do this communication step, we already have the two pieces of the matrix ready for the next step. The next step is the dropout, and in the first part of the dropout, as you can see here, we do a matmul, and then we apply a dropout, which is still a nonlinear function. So now, since we have these two pieces together, we can apply the first approach, not the second. So we can, we already have y splitted by columns. So our y is y1, y2. Now we can just split the weight matrix of the dropout B into rows. So B1 and B2, like this. And now we don't need a communication step because we can just do y1 multiplied by b1 and y2 multiplied by b2. And this time we need the communication step after these two matrix multiplications, because then we have to compute the dropout and produce our output vector z. So as you can see here, we are basically avoiding one communication step, which would be right here. We are avoiding a communication step here, which is not needed because in the dropout layer later, we already have the two pieces separated, so we don't need to gather them at first. That's why we delay the gather in the first part of the multi-layer perceptron. So this is why the second approach is better in the first part of the multi-layer perceptron. So just to be clear, I want to specify something that might be a little bit confusing. In this case, in the first part of the MLP, we're going to apply approach number 2, which is this one that I explained here. And in the second part, we apply approach 1. Which was the first one. And so we apply both of the strategies of splitting the weight matrix. The thing is that by doing it like this, interleaved, we are avoiding, as I said, a communication step right here. Another thing that I want to specify is that there is this f function right here. And you probably already noticed that it has the same color and shape of this G. That's because, as I said, G is all gather. Well, we can call it all reduce. Another thing that I want to specify is what this f does. So as you can see, this f has the same shape as this G. But it actually behaves a little bit differently. So this G is all reduce. That's because it takes the output of the first and the second GPU and it just sums the two matrices and produces a matrix that will be dropped out later. So this is all reduce in the forward pass. But remember that when we do the forward, then we also have to do the backward when we are doing the training loop. And in the backward, what we need to do, if we want to do it in parallel, we need to do an all gather, so or reduce in this case, also of the gradients. So the gradients are backpropagated together like this, so in a parallel flow, literally just the other way around of the forward. But at the end, we need an all gather of the gradients right here, because we need to join the two streams of gradients. And so this f right here is going to be an all reduce, but in the backward. And both of these functions are going to be an identity function in the other step. So for example, g is an identity in the backward, meaning that it does nothing, and f is going to be an identity in the forward pass. In fact, if you see here, like x goes in f and x goes out of f, so it does nothing. So this is how you parallelize your multi-layer perceptron. In the Megatron LM paper, they also show you and go through the self-attention operation, but don't worry, it's basically the same. The only thing to keep in mind is that in the multi-head self-attention, each head will compute, will have its own key query and value matrices, and they will just work in parallel. But then the rest here, it's the same, as you can see, for the dropout. So definitely go through this paper if you want to understand these things, to understand the details of this, and maybe also go through the code if you think that it's necessary. So basically, then the last thing that I want to say is, if we combine the multi-head self-attention and the MLP layers, and we just look at one transformer layer, we have a total of 2 communication steps for the forward pass and 2 communication steps for the backward. So this is a total of 4 communication steps, so 4 collective communications per transformer layer. So this is very important to keep in mind, and nowadays, for example, people are trying to work on different kind of parallelism strategies to reduce this overhead, and maybe try to basically just try to remove some communication steps to make things more efficient. Okay, so at this point we finished the topics of today. I really want to thank you if you reach this point. It's a pleasure for me to make these videos, and it's also very useful because it makes me understand if I really understand the things that I'm explaining. So definitely leave a like or a comment or some feedback, everything, if you want really to make me improve over time. And thank you for watching, and see you in the next video.